right, we can jump into ensemble models. Okay, so we'll see how far we'll be able to cover ensemble models also today. So decision tree regression is very simple. Yesterday we almost all covered everything. Say in the decision tree classification, we were actually looking at probabilities to find out the best feature, and then we are splitting the data, right? But in decision tree regression, we will actually look at the averages of the target variables based on the cut point. Right? I said cut point, right? You take this column and take distinct values from it. Take this value, try to divide data less than and greater than and equal to. See how what is the average of all the records falling in less than and greater than that number. Okay. Again, look at the error. On a regression problem, what is the error metric? Maybe RMSE, maybe MSE, maybe squared error, right? Squared loss. We look at the loss. So you are getting it, right? So I have taken this column, took this value, divided the data into two parts, less than and greater than or equal to. Whichever records falling less than, I took all those records and then took an average and set that as prediction for all the records less than, in this field, this value, and the average of all those values I took as the prediction, and greater than or equal to all those target variables I took an average as the prediction. Now I have predicted values and the actual values. I'll look at the difference or the error I'll calculate, keep it aside. Take this data point, again do a split, collapsing of data, and then take the averages of the target variables. Again look at the error. Right? So I'll show you clearly, right, on this. So like that, right, for every feature you try to calculate at different cut points, you will try to calculate, you try to look at the error wherever which feature gives you at a given cut point the less error, you take that as the best feature for now. Okay, and once that feature is done, you will eliminate that feature and take the other features to try to do the cut point. So a simple example I have taken, this is a baseball players data set, hitters data set, and we need to predict the salary by looking at all these features. But for simplicity, I have taken hits, years, and salary. Okay, and this example and whatever this thing, whole thing was taken from Fundamentals of Statistical Learning. I think that's the book. Give me 1 second. This is not, sorry, this is Bing, right? Yeah, this is the book. Introduction to Statistical Learning. Right? Don't buy it. No, there is a PDF out there on the internet. Right? It's a 400-page dark book, but no need to read. I actually read through it, and it covers machine learning in statistical perspective. Okay, in that they have given this example, and this example now sounds very good. That's where I took it from there. Okay, so here hits, years, and salary. I have taken two input variables and one output variable. Okay, if you look at this data and try to do some analysis, that's a kind of building model, right? If you look at this condition, right, hitters data years less than 44.5, and I have taken salary and mean for all the records whose years of experience is less than 4.5 years. I'm going to predict this as the prediction. Okay, And if it is greater than or equal to, right, I have added one more feature, right? Here I am using years, and here I am using years and hits also. One more feature. And then if it is greater than or equal to 4.5, then I will consider the hits. If they are less than 117.5, then I take, this salary as the prediction, right? If greater than 4.5 and greater than or equal to 1.7, right, then I'll take this mean as the prediction. So if a record comes in, I'll look at that record's years of experience. If it is less than, I'll predict this. If it is greater than, then I'll consider one more feature, one more column, and I'll have a cut point again, right? And then I'll take this as the prediction and predict. Okay. Why do I come to this conclusion on this particular data? Because with these kinds of cuts, or with these kinds of nodes, the training data is giving less error. Okay, this is one prediction, this is another prediction, this is another prediction. For some records, this is going to be the prediction. For some, this is. For some, this is. When I calculated out of all the cut points, right? In the hits, there will be many cut points. In the years, there will be many cut points. Out of all those cut points, right? First, initially, I took years, looked at all the cut points and calculated errors, kept them aside. 4.5 is the best cut point where I got less error. Now I splitted data into two parts, right? Tree got splitted into two parts. On this part, I left it alone. And on this part, I took hits as one more, column, and then again splitted the data using different cut points. Again calculated the, the predicted values, and then looked at the error. And out of all the different cut points, right, this 117 came out to be the best. That's where the tree is like this. Got it? On a regression problem, how the prediction is happening, how the tree is being built. Did you get it?
Yes, sir. But I don't know. Will it be accurate, sir? When I say accurate, we're just going by the real data, some specific values, and then branching those.
Yes.
So,
Yeah, if you use one decision tree, maybe may not be. But when you are using multiple decision trees, that the ensemble model, then definitely it will work. There are some problems with it. It's a greedy search, right? Greedy search means when it is actually trying to split when it is trying to split the data on years. First time when it is trying to split the data, right? It took this column, looked at cut points, tried to make predictions, looked at the error, took this column, looked at different cut points, took the predictions, took the error. This column, like that, all the columns it looked at, and it came down to years as the best column. Okay, it splitted the data, and then in the down below, right, it will never consider years again. Okay, and maybe after splitting, five six uh, levels down, if you do another cut on years, maybe you will get best accuracy. We don't know, but this decision tree regression is not having that facility. That's a greedy set, we call it as. That's another problem. That's one of the problems where Girigar is actually trying to highlight. Got it? Adhayanandi?
yes, sir.
It considers a column at one time only. Down below it will not consider the column again.
Yeah.
Mostly, right? Sometimes it may, but 99% of the times it will not. Greedy sets it is. It will not consider. It's a greedy. It's a problem in decision tree algorithms. Okay, so that's how it works. Right? That's how it works. The model will predict salary of players based on below conditions. If years of experience less than 4.5, prediction is equal to average salaries of players with years of experience less than whatever. If it is greater than, it looks at hits and then takes the average of all those salaries which are between, for records which are between these two conditions. Greater than, which are between those two conditions, like that it is, whatever I explained. So ultimately, if you want to look at visually, right, it looks like this boxes. Right? R1 is less than 4.5. All the records falling into this area will have one prediction, average of all the y variables. All the records falling into this area, right, greater than 4.5 and greater than 117.5 will fall into this rectangle. So it is going to divide the data into multiple rectangles. Okay, so yeah, I'll talk about that later, but I got something into mind. Okay, see, leave it. So it is going to split the data into boxes or regions, we call it as. Okay, R1 is equal to X for all years greater than less than 4.5. Mathematical notation it is. Okay, R2 is equal to X for all. No, this is for all, right? This is for all. Given. Sorry, this is given, right? It's like probability. X given y less than 4.5. X given y years greater than 4.5 and hits less than 11.7. X given, right? Given means this condition is true. All those x's, right, fall into R3. This condition is true, right? All those x's fall into R2. This condition is true. All those x's fall into R1. This is mathematical notation. Okay. Probability also the same way we actually see, right? So there is no probability here, but mathematical notation it is. The points along the tree were the predictor space internal nodes. Okay. The points along the tree where the predictor space is split are referred to R. These are internal nodes to R3, these are internal nodes to R2, these are internal nodes to R1. That's not needed. It's a terminology. Okay. The R1, R2, R3 are called as terminal nodes or leaves. Right? In here, the leaves have got lot of data, and while predicting, right, it will come to the leaves and take the average of the y variables and make prediction. Okay. Example tree representation of it's a mathematical notation kind of thing. X1, X2, X3 like that. The different features it is splitting on. It is trying to choose the best feature based on the cut points. It tries all the different distinct values and finds out the best cut point. So this is the mathematical notation, whatever I am talking about, right? We now discuss the process of building a regression tree. Roughly speaking, there are two steps. Right? Algorithm divides a predictor space, that is the set of possible values x1, x2, and so on xp into j distinct and non-overlapping regions. The terminology is very important. Okay, in interviews or maybe while reading an article, this terminology is important. So you try to read and remember. These points are good enough. Okay, try to read and remember. So set of possible values, samples, right? X1, X2, and so on xp into j distinct. R1, R2, and so on R3. Here Rj, right? For every observation that falls into Rj, algorithm makes the same prediction, which is simply the mean of the response variable. Okay, Rj. So this is the example. How to select the best predictor to split? Right. This is the question I already answered. Right. The value is 4.5 in years. How did it select? Algorithm takes a top-down greedy approach. That is known as recursive binary split. Okay. So it's a CART algorithm, and it does a recursive binary split. Here there is no ID3. Basically, on a regression problem, it is CART only, recursive binary tree, and it takes a top-down greedy approach. The approach is top-down because it begins at the top of the tree, at which point all observations belong to a single region. Right? Beginning, all observations belong to one single region, and then successively splits the predictor space. Each split is indicated via two new branches further down on the tree. Right? I think it splits into two. It splits into two like that. Right? That's what it is. Greedy because at each step of the tree building process, the best split is made at the particular step, at that particular step, rather than looking ahead and trying to see in future if you have any, better split, or there may be, if you do a different split here, maybe down below you may get a better split on the other column, but it's not going to look at it. There is no way, basically. That's where you characterize greedy split, greedy, and sometimes it may cause problem, but most of the times it works. So that's where these algorithms are famous. These random forest bagging, boosting, all these algorithms are dependent on trees only. Tree algorithms are very famous and very efficient in making predictions, even in non-linear spaces also. Right? If you look at this, it is actually doing a boxes kind of a thing. But for non-linear, decision boundaries and non-linear regression problems also, it works well. I'll show you when we actually use the ensemble models. So how to build a model? Decision tree regressor. And I took the data, cleaned housing price data, and then splitted data, and you all know this decision tree regressor object I created and fitted the model and looked at the accuracy. It gave me only 74% R1 R square, but linear regression was working well than the decision tree, right? Why that? Because if it is a straight line split, so the decision tree is actually doing boxes kind of a split, right? If it is a straight line split like that, or data is in a non-linear fashion, and then it's having an angle, then you need to fit the data through that angle. But this boxes thing, right? It will cause a problem there. This problem also can be avoided when we use the ensemble model. So the point I am trying to make is decision tree best or the linear regression best? It depends on data. Okay, but when you use the powerful models like ensemble, right, they will work both, both ways. Whether it is a linear separable boundary or non-linear separable boundary, it will work the best. Okay. So randomized set CV I have taken, where instead of in grid set CV it will take all the combinations, but randomized CV takes 10 combinations randomly and then tests and finds the best parameters. So there I have got 87% accuracy. On the test set it is actually 73 only. That means model is overfitting. When model is overfitting, we may have to use that cost complexity pruning alpha parameter, or the max samples, min leaf nodes, and those kinds of parameters, and play with the model and make the model the best. Okay. So that is the decision tree regressor. Any questions here?
Sir, first when we built the model first, can you please scroll up? There, did it internally? No, not there, sir. In the code.
This one?
In the code. Below that, we built a model, right?
Yeah, here.
Yeah. So please come down. Please come down. Yeah. When we built the model here, finally we got that. So that internally did the selection of a best feature. All those things it's done already.
Yeah, that process only we are trying to understand how exactly that split was done. You just created an object and then said fit. It did everything, and you are predicting. Right? Okay. So how in interviews they will ask, basically they'll ask questions on SVM, and they'll ask questions on this decision tree, and they'll ask questions on the imbalanced data set, right? And linear regression assumptions they will ask, and confusion matrix, the precision recall F1 score, and which to use where, and these questions they'll ask mostly. Overfitting, underfitting, high bias, low bias, these things are going to be definitely there. Okay.
Yeah. So later, what did we do here, sir? After finally getting a model, we did the predict, and later what did we do? We try to do some randomization and all. What is that? Can you tell us?
There is no randomization, sir. Once we predicted, we are looking at the accuracy.
That's done. That's done at 0.4. What is that below that?
This is a grid set CV, alternative for grid set CV, randomized set CV. I already explained, right?
Okay, the
Grid set
previous one.
CV, you remembered? Grid set
Yes,
CV,
yes, yes.
right?
Yes.
Randomized set CV and alternative for grid set CV, but the difference between randomized set CV and grid set CV is grid set CV will take all combinations and build all models and then find out the best features, right? Grid set CV. Do you remember that?
Yes.
But randomized set CV will take 10 random combinations of these three different hyperparameters.
Sure. So
And
you
then
are
test builds only 10 models. And out of those 10 models, which one is best? It's going to give.
okay. So basically, for comparison sake, you have put it here. So.
To find out the best model.
Okay. Got it.
To find out best cross validation and all that use and then find out the best model, I have used randomized set CV. In randomized set CV, you can specify the number of combinations it should randomly pick. There is a parameter there. I forgot the parameter name. By default, it is 10, but it can you can specify. Yeah, estimator. No, it's not estimator. Sorry, this one, annator. Right, default 10. But if you specify 100, right, out of those all combinations, it will choose 100. So how many I can have here? Random int, right? Low 0, high 200. Random int will generate random integers between this range, I think. Forgot. Give me one second. Generate 200 numbers, I think. Yeah. How to get values out of random int? So give me 1 second. It will generate the distribution actually. Low, high, random int. Uniform distribution it will do. And how to get the values out of it? How to get values out of it? RV. Probability mass function.
What's the method we are using, sir? Rand into dot.
Rand into dot. I am not using any method there, but I don't know how this is getting. Maybe in the randomizer set C there is something which is getting the data there. I did this long back, so ri.pmf will give you. What? Three parameters it needs, low and high. How is it taking that low and high? I'm like, randomized set series take what? Two positional arguments, but 4 were given. Here I gave 4. NP that array. Maybe internally this is actually this randomized set CV is accessing these, but how it is accessing? Still rand into data PMF RI I'll say here. Low high 1 2.
Yeah, probably we can look at it later, sir.
Later,
my question is not about that. My question is after initial model we arrived at, then we used this randomizer search, and from there, did we do recalculation of the decision tree?
This one.
Yeah, that's where I'm asking.
This is like grid set CV only. It will pick the values from here, right? Max leaf nodes one value, max depth another value, min sample leaves another value, and try to put it into the decision tree. Build a model with the cross validation 5 and keep the scores aside. Again, take another value, another value, another value, build a model. Another value, another value, another value, build a model. Like that, it will build models, multiple models. Keep the scores aside. It chooses the best one out of all those and gives you the best hyperparameters.
Yeah, so my question is, we have only currently, I think, 2 or 3 columns. One is hits, years. So in such case, how we can vary the max depth and all the different nodes and all, because we already going for binary. So we already know it's probably 4 or something like that is the nodes that we can come up with. So are we going to do multiple splits within the each column? Probably
no, if it reaches the maximum depth, right? If you give a number bigger than the maximum depth it can go, it will not go. Right?
No, basically my point is how we can go to here. We put max depth range rand into 1 to 100.
Yeah.
Because now, let's say years, we are only taking one split, that is some number of years less than or equal to and greater than, only 2. So in that case, the depth which will be contributed by years will be, let's say, 2. Similarly, one hits is the another one. Let's say it gives maybe depth of 2 more. So total 4 depth or something like that.
Only 2 depth it can go. First column to 1 depth and second column 2 depth, right? But if you see extrain, I would have taken the total data. That's where maybe I gave. No, this is not that data actually. This is a housing price data set. It has got around 100 columns there.
Oh, okay.
Maybe I was columns only. No, there's no need to give that. But you know this rand int, right? It is not giving any output there. it is actually generating some object there, and I am unable to process that object and see the values there. That's the problem I am struggling with. We'll see later, right? So you see, right, how what is the object it is generating and how to extract values out of it.
Yeah.
Mean variance, skewness, kurtosis.
So maybe it is using randint.stat.genint.
Random dot.
Stats dot.
Shall I try that?
Just give it a try.
Random dot.
Stats.
Is that right?
Stats dot 1 second. Genint.
Gen.
Genint.
Gen. Method, is that a function?
Actually, randint. Scipy dot stats dot randint.
I create an object right there that like same. Scipy is not different, so I need to import scipy here. Hmm. The above thing and this one are same. Right, low and high are needed. Low and high I gave, and it is just giving me an object, and now somehow this randomized set CV is getting those values. Right, uniform distribution. I am unable to see. There should be a way to see that. TMF probability mass function or probability density function, right? So probability mass function. Okay, we'll see that later. Okay, leave it. Okay, so here, right, I wrote that whole thing in a equation thing, right? I say R1, R2, and so on, Rj. RSS we calculate like this from region 1 to J. In each region, we will calculate the error. What is the error? Squared error. Yi minus Yrji. That is like average of all the y values here on this particular region. Right? There are 10 regions. There will be 10 this kind 10 averages. Right? 10 averages, and for each region there may be maybe 100 or maybe 200 records in each region. Right? 200 records minus that square, right, and sum it up, and then from j is equal to 1 to j is equal to 1 to j. Right, so all those regions it's going to sum up. This is the total error. So every time it does this, it takes a cut point S and try to split the data into the regions Ri, R1, J comma S and J comma S, right? So it is going to split the data and then calculate the error, right? Whatever we understood, I try to write it in a mathematical notation here. Okay. So did I went a little fast? Would you like me to explain this again?
Yes, sir.
Tell us what is YR, how is YR calculated?
Why R?
Yeah,
That's the
YRJ.
average. That's the average of that particular region. Y value average of that particular region. Yi belonging to Rj, that region's average is going to be Yrj.
Okay.
So we have seen that, right? In the top we have seen it. Sorry, not top. Oh, the diagram is not here. So here, right, In this region, there are some data points. In this region, some data points. In this region, some data points. We take y values of all these data points and take average. That is, region 1's are, the RJ. Okay, YRJ. Region 1's YRJ. Region 2's Y1J, Y2J, Y3J. Y1J is the average of all the data points Y values in region 1. Y2J is all the average of all the Y values in region 2. Y3J is the average of all the Y values in R3, region 3. Okay, so you take this data point and take Y of it, and then take the average of this region's Y, calculate the distance, all the data points, you calculate distance and square them and sum them. Keep that aside. Again, square them and sum them, keep it aside. Square them, sum them, keep it aside. And sum all of it. That's the equation. That's this equation. From J is equal to 1 to J, first region you calculate squared error. Second region you calculate squared error. Third region you calculate squared error. All those errors you sum up. That is RSS. Got it? Got it?
Yes.
Right? This RSS is calculated for every cut point. Right? We consider all predictors x1, x2, and so on xp, and all possible values of the cut point S. For x1, we'll take a cut point, try to split the data, and calculate RSS. For x2, we take a cut, another cut point, try to calculate RSS, keep that aside. Another cut point, try to calculate, right, at a cut point and give. Out of all those, you take the minimum and keep it aside. For x1, which cut point is giving you the minimal error, the cut point and the error you keep it aside, or the algorithm keeps it aside. And again, it takes the x2 and takes the cut point. Right? This is that R1 J comma S for all x that the x that satisfies this condition, and R2 region that actually satisfies this condition. What is this condition? Xj less than S, Xj greater than or equal to S. Okay. So if there are categorical values, right, in this particular column, it is going to do the probability calculation, right, the conditional probability, right. For all, I'm actually maybe jumping the guns and trying to confuse you. Give me 1 second. So this thing, right, this point is clear, right? This mathematical notation is clear. Do I need to explain that again? This particular mathematical notation, is that clear?
Please explain again, sir.
So when you take a cut point S, right, suppose that 4.5, okay, the data is going to be split into two parts, right? X that satisfies Xj, right, for each X, right, that satisfies less than 4.5. S is 4.5 now. Okay, region 2 is going to be, region 1 is going to be less than that data, that cut point. Region 2 is going to be greater than or equal to that cut point. That's it, right? Simple. Got it?
Yes.
Right? So mathematically, I'm showing that's it. This is understanding. This is also important, because when you look at some articles in future, right? Maybe there will be some mathematical notation. Not to get confused, I just embedded this. Okay. Mathematically, I am showing this here. Then diagrammatically, we have seen it here. Here less than 4.5, this is one region. Here greater than 4.5, there is another region. In this region, there are data points. In this region also, there are data points. I am showing you the average of the Y value, average of the Y value, average of the Y value. But there are data points. So those data points, I am showing it as a set here. Set of all X that satisfies Xj less than S. Set of all X that satisfies Xj greater than or equal to S. So there is going to be two regions for one cut point, and for these two regions we'll calculate the first data points average, first regions average, second region's average, and I have to put a square here. I forgot to put it. Right, I need to square that, all those squared errors and sum it. I need to put a square here. I forgot to do that. Right, this equation, right, I tried to show it here. Okay.
Yeah, actually,
So,
what was confusing was that under you put it, right. So we
Ah,
thought I was somehow I did not see properly and thought that it's a single equation
yeah,
giving R1. So if you can bring that
logical.
R, yeah, I thought it's
It's like a
logical and
logical
you can
operator.
bring
But
that down, right? So
yeah,
maybe I'm just saying.
if you read this whole thing, right, it makes sense. We consider all x1, x2, and so on, and all possible, values of cut points as for each of the predictor, and then choose the predictor and cut point such that the resulting tree has the lowest RSS. What is the tree? This is the tree. This is one branch, and this is another branch. Even my explanation was wrong. So I was actually I'm jumping the guns. I don't know why. Okay, and then and we seek the value of j and s that minimizes the equation. Here I need to have a square. Let me go back to that. Let me correct it. To put to square, I need to put this there. It's a very tedious process. Rj, yeah, that's the last one, right? Yeah, yi r sigma, very sigma. Sigma sum here. Yeah, here. Yeah, that's it. Right. So that's the this part. This particular part is what this is. Okay. And then for all the regions we'll do that. And then that's considered as the total error.
so here R2 is again divided into two regions, right?
Again R1, R2, R3, R4.
So the error will be calculated for every split.
For every split it will be calculated. And we'll choose the best split, which gives you less error. It's going to be a very tedious process of splitting the data into multiple. For every split, there is going to be too many calculations, right? It need to choose different cut points. If there are 100 cut points, right, 100 times it need to split the data and calculate the error and see which cut point is giving you the best error and choose that as the cut point and split the data into two parts. Got it?
So how to choose here whether to split R1 or R2 in the next iteration?
That is again the cut point based only. In R1, it will do all the, take the other columns and try to do cut points and see. If we do a split on the, that's a good question. See this here. There is a branch here, right? Original data was split into two parts here, right? Based on years. There are some records here, there are some records here, right? In both records, there are multiple columns. All columns are there, right? In both splits, right? Do you agree?
Yes, yes.
Right? In those splits, right, it will do cut points here and cut points here also. Wherever it is getting the less error, that side it will cut using that particular column. Got it? No?
So it actually takes all the columns except the years.
Yeah, while doing the cut here, right, while calculating the cut points, except years, it will try to take the other columns. Except years, it tries to take other columns. Maybe years also it can consider, but it said greedy, so I am thinking it is not.
So here in this case, the right side data,
Hmm.
in right side data, hits is actually giving less error. That's why it is cutting.
It is cutting on this side.
Okay.
Yeah, right side subset, on the right side subset, hits is giving the hits at this cut point is giving less error. On the left side subset, there is it would have tried, the algorithm would have tried all the other columns, but it couldn't find, right? Yes, basically in this data only 2 columns are there, but it would have tried all the other columns and it couldn't find a best split there. The error is high, overall error is high, so it went in this direction.
So once it went into the right direction, once it went into R2, so it won't come back again to R1 to split, right? It
No,
goes
will
back
not,
to the
because
same.
it already tried all the cut points, and then it would have seen that it's not worth doing a cut there.
Okay.
Sir, I do not think so, sir, because for example, if we get a new record which has let's say years of 3 years, and then it obviously has to come to the other side to predict.
Yeah, that is in a decision tree. That's a problem. When you change the data, tree structure will change. Again, calculation will happen altogether from the from the beginning. You're talking about adding new record, right?
Yeah, when we need to add a new record to make a prediction, in that case, obviously because model is already built, obviously it will traverse through the other one and then do the prediction.
Prediction, yeah. But if you add new record to the data and try to rebuild the tree structure will change completely.
Agree, sir.
So if a new record has the experience of 3 years to predict, so it directly goes into the left node, right? Region 1 and predicts it.
Yeah.
Yeah, that is the reason why I said the accuracy may not be appropriate, because it's
Yes.
just branching out on just one point.
Yes, but if your data is huge, then accuracy will be appropriate, because on a huge data, if you take averages, right, they are going to be appropriate. On small set of data, the averages may not be appropriate.
Yeah.
Right? And if you have too huge data in millions of records, algorithm cannot handle. The memory is not sufficient. And different problems there. Okay. So I would stop the class here, and Monday we'll look at the ensemble model. I would recommend you to practice a little bit, right, and come back. Okay.
Thank you, sir.
Thank you.
So,